we're supposed to do bog and wet marshes, or just bog, or did you want them all to be included, or just one type?
Let's see.
There's like 47 bogs and then like another 15 wet marshes or wet meadows included in the data set.
Yeah. Well, since I didn't, why don't you just do the bogs?
Okay.
Keep it a little more contained. Okay. So what we're moving on to now has really nothing whatsoever to do with the previous section of the class. But our goal over the next few weeks and perhaps longer, we'll talk again at the end of today about where we're going in the last part of the class, is to look into how to analyze spatial data. And so if we look at a map like this, so here's a bunch of points, and there's a variety of questions we can ask about spatial data. First of all, so the first set of questions we could ask is about the actual set of locations of those points. Okay. What pattern, if any, is there in these points? Is it a random pattern? Is it something other than random? And if it's not random, in what ways is it not random? And that could be, these points might represent the location of individual trees, and so if they were random or non-random, that might tell us something about interactions between trees. We could also ask what generally controls the distribution of points, right? If there was, seems to be a high density of points down here and a low density of points up here, right? Does that represent, if these are trees, does that represent some, one or more kind of environmental factors that might control where trees can grow, right? And that would be one reason that would be interesting. It's interesting from a fundamental ecology perspective to understand the biology of the species of trees. But if we were, say, asking about what might happen to this species under climate change, right? We would need to develop a model of how, where the trees are now and how that relates to various climatic variables as well as topographic variables and soil variables and so forth, so that we could then predict whether, under climate change, some of them are going to move, say in this direction, right? So these could be, trees. These could be sort of more generalized. These could be populations. Those are the kind of certainly ecological questions that could be asked about where these points are, right? So this is meant to be a map of occurrences of something. And we want to understand why it is where it is. Another possibility for a set of data like this is that these aren't actually occurrences of something of interest. These are actually sample locations. Okay, so we've gone out into the environment and for one reason or another chosen each of these spots to take a sample of something, to measure something. And then we can ask, well, how do we, so suppose we're measuring something about soil chemistry, and we have measurements here, 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 and here. How do we estimate what the soil chemistry might be at this intermediate place? Right, and because for most of the things that we're interested in sampling across space, we can't sample absolutely every single location. This question of interpolation, or sometimes called smoothing is a really important one, and it's a big part of spatial analysis. And then we could also ask, suppose actually we measure two variables at each of these points, and we think that there's some relationship between them. So that we can do, so we do say a regression model which says that, well, what could it say? I mean, it could say that soil pH is a function of how much rainfall there is. We can do a simple regression, but the simple regression assumes that each of these observations is statistically independent from one another. But in a spatial context, it's likely that whatever's going on here, whatever processes are going on here, are similar to the processes that are going on here. And remember that in regression, the stuff that's buried in the error term, right, is not just randomness. It's all the other factors that matter that we haven't included in our analysis, and some of those factors are likely to be similar next door as they are here. So there's going to be a problem of non-independence, and so incorporating spatial dependence in regression analysis can actually completely change the outcome of your predictions. Okay, so these are the kinds of problems that we're going to be addressing in this part of the course. So we'll actually start with this. We'll come back to the spatial pattern a little bit later. But this data set, these points actually come from a data set. They are soil sample locations. So here now they are on something that approximates a real map. So this is a river in the Netherlands called the Meuse River. And this is a floodplain in the bend of the river. And around this site is a whole bunch of, there's a village there. So there's a whole bunch of people living around there. This is Western Europe, so there's a whole bunch of people pretty much everywhere. And so in this floodplain in the bend of this river, they've done a lot of soil testing for heavy metals. Okay, and so what we're going to be looking at today, or the rest of the day, is asking, what is the spatial pattern of heavy metal concentration? Can we interpolate it to places that we haven't observed it? And what can we understand about that spatial pattern? So here are the four things they looked at: lead, zinc, cadmium, and copper. And these are all plotted on the same scale, so the darker the dot, so each dot is one of those sample locations, the darker the dot, the higher the concentration. We can see, for example, if we look at zinc, there seems to be higher concentrations along this edge, which remember is the edge of the river. So there's higher concentrations where the river is. Yeah. Anybody know about pollution in European rivers? Okay. So what about them? Well, I mean, I could make up a story about industrial pollution, but I don't actually know any details. So,
I mean, I know like Port of Rotterdam is like one of the most polluted waterways in the world, pretty much, because there's so much upstream industrial activity. Even though it's regulated, it's just the intensity is controlled. So.
And this river actually, it comes through from northern France, goes through Belgium and into the Netherlands. So I don't know exactly what the upstream activities are, but I assume there's some kind of industrial stuff upstream that's in the water. So, so we can sort of see this pattern. These are all plotted on the same scale, and what we can see, for example, is there's a lot less cadmium than there is zinc, but this makes it rather hard to see what the cadmium patterns are. So if we standardize the data, so by standardizing, we've taken each of these data sets and rescaled it so that it has a mean of 0 and a standard deviation of 1. Okay, so each data set now is on its own scale, which is, well, it's really a z-score for each observation. And now we can see that, in fact, in all 4 of these metals, there does seem to at least be this pattern where there's heavier deposition or higher concentrations along the edge of the river. Let's see.
Bruce?
Yeah.
When I got everything you said except the mean of 0. So is that you comparing with the background, or?
Well, no. I mean, these values don't have any. Yeah, these don't have any intrinsic meaning anymore, right? Well, all we've done is, whatever the scale is, whatever the range is, but whatever the mean concentration is, right? We subtract that mean from each data point to get a new mean of 0, and then we squeeze the variation down until we get a standard deviation of 1. I had some notes that I printed out. I forgot to pick up, so I'll just have to remember what I meant to say. So, if we think about, let's think about zinc, for example, and let's first just start with the problem of, we have this spatial pattern in zinc. We have these observations at every point. There's variability, and suppose we want to predict what the value of zinc would be if we took a sample here, or if we took a sample here, or if we took a sample here. Okay, and I don't know why they sampled in the places they did, but if you imagine, this could represent, the sampling scheme might be very expensive, and that's why they didn't sample everywhere. If you imagined, well, suppose this was a much larger scale, and you wanted to know, well, should I do a development here? If I do a development here, is it going to be a place that's subject to high metals contamination? Or what's if I want to sort of do some kind of cleanup of the whole site, where should I concentrate my resources? Obviously, we want to concentrate where the contamination is highest. How high is it likely to be in here? Okay, so that's sort of the general question of why we want to do interpolation. So, what does it mean to interpolate? Okay, we have a bunch of observations. We know what the zinc concentration is in each of those places. I go to a new place. What's my best estimate of what the zinc concentration is going to be at the new place?
Will be based on what the known concentrations are in proximity to that place that you're looking at. So their magnitude and the distance from the point that you're looking at.
So I think Freud talks about some Tobler's laws of geography. Anybody here talk about that? It's like the first law is I look like my neighbors, something like that. So if we imagine, for example, just for simplicity, let's look at a one-dimensional map, right? So here's space, say it transects across the site, and here's a bunch of observations, and there's a pattern of variability, and if I if I pick a new point here and say, what's my best guess as to what the value of y is going to be at this value of x, right? There's a bunch of different things I could do. I could ignore the spatial information and just take the average over the entire domain, right? That would be one step better than just drawing numbers out of a hat. I could say, on the other extreme, I could say, I'm just going to look at my nearest neighbor and say I've got the same value as my nearest neighbor. Or I could look in some neighborhood and say, well, I'm going to be some average of values in my neighborhood. So then the question is, well, how big should I make the neighborhood? And more generally, should I wait, even if I look at, say, this neighborhood, and I'm here, should I give more weight to the nearby points than to the more distant points? Okay. If I was to do a neighborhood of 2, look at my 2 nearest neighbors, and then do a linear weighting of, the point that's twice as close has twice as much weight, then I'm just going to draw a line connecting them, and wherever I am on that line, that's the value I'm going to predict. Okay. If if I have a larger neighborhood, then I'm going to want to somehow take into account information from these values that are farther away, and so on. Okay, and so part of that decision, and we'll come back in a little while to quantifying how you decide what's the right neighborhood and what's the right weighting scheme, or not how you decide, but how you evaluate, is sort of what you believe about this pattern of variability. Okay, and in particular, do you think that there's, that there really is a pattern in the landscape that looks like this, or in which case you'd want to really focus on your nearest neighbors as having the most information, or is there kind of a general pattern like this, and all the variation around that general pattern is noise, and the noise here is independent of the noise here. Okay, in which case you're going to want to try and focus in on this large-scale trend, which is going to require the information about that trend comes from looking at a larger neighborhood. So we'll sort of look at some different ways of thinking about that problem, how you decide on that issue. But for now, let's take a geographer's view of this. The primary indicator of how important a point is, or how important, how much information a point is distance from me. And well, before we get that, so implicit in what I've been talking about is that we can, if we have a point I where we have no data and we want to predict the value there, we basically take a weighted mean of information from the other points. Okay, so the W's sum to 1, so these are weights, so I guess there is a little bit of connection with what we've talked about last time. But the idea is, obviously, points that are completely outside my neighborhood that I'm not going to consider have a weight of 0. Points that I think are very important or very relevant are going to have a high weight. And so, if we're focusing on question of distance, kind of one natural way to think about using distance to decide which points to weight more highly is called the inverse distance weighting. So, this denominator is just a normalization constant to make sure that the W's all sum up to 1. But this just says if the distance between the point I'm interested in, I, and the one I'm looking at, J, the weighting I'm going to give declines as the inverse of that distance. Okay, which will look something like right. So the weighting, right, is going to be some kind of hyperbolic function like that. Okay. And that's, you can, I mean, that's, why a hyperbolic function instead of a linear function. It's just, it's related to, I guess, how you think about dispersal of organisms or chemicals or so forth. It sort of relates to, you can probability of movement of a chemical over a distance. Now, it actually can be generalized. You can put an exponent around this. Okay, so if P, well, first of all, if P is 0, then in fact 1 over d to the 0 is 1, so that weights all points equally. Okay, so you actually can get, just let's forget about spatial pattern, let's just look at the average concentration across the whole study site. As P gets very large, the sort of limit as P goes to infinity, then the because this quantity is less than 1, the closest point is going to have all the weight. Okay, so you can actually get, so by taking P be very large, you can get the rule just look at the closest neighbor. And then the values of P in between, just as you increase the value of P, you just get ever steeper weighting functions. So the higher the value of P, the more weight you're putting on the closest neighbors. And one thing one aspect of this inverse distance weighting scheme for interpolation is that if I'm actually asking about a point where I have a measurement, right? So if dij is 0, what do we do with 1 over 0? Well, we can make an arbitrary rule, or in fact, if we just take the limit as the distance goes to 0, it turns out that if you take that limit, then all of the weight will be, regardless of P, as long as P is greater than 0, all of the weight will be in that one point. And so you'll actually get, if dij is 0, you'll just get zi equals zj. Okay, so it truly is an interpolation scheme in that the predicted value goes through the observed points. So here is the result of applying this to the zinc. A couple of things about this map. So first of all, these white lines don't mean anything. They're plotting artifacts that I could figure out how to make it go away. The circles are the locations of the samples, and the size of the circles represents how much the measured zinc concentration there. And then what we've done is we've taken a grid, and you can sort of see the size of the grid by these little boxes, and used inverse distance weighting with a p=1 to predict the zinc concentration at each location. And white is a high prediction, red is a low prediction, and this is what I did before I did the predictions is I did the log transform of zinc. Okay, so I'm predicting the log concentration. Simply because, well, there's a number of reasons why looking at logs of concentrations makes sense in terms of, the chemical, the way the chemical reactions and so forth. But it's also, by making that transformation, it sort of, it makes the whole surface a bit smoother, because without that transformation, we have really tiny, values of, 20 here and values of 50,000 here, and so by sort of squeezing down some of that variability, it makes the surface a bit smoother and a bit easier to fit. We can certainly always back transform once we've got this fitted surface. But what we see is that, it looks about right, looks reasonable, right, in areas where the values are small. We have our predicted value is relatively low. Up here along the coastline, where we have lots of high observed values, we have pretty high predicted values. Okay. So, so I can say, well, if I was to go right there, my prediction is that, where are we? 6.2 is the log of concentration. Yeah.
Did you do this in R?
I did do this in R.
Do they have sort of pre-made statistical tools for spatial analysis? Do you have to write first?
No, there are statistical analysis tools in R, and we'll actually look at those in.
I mean, yeah, spatial statistics.
Especially statistics in R. Remind me again, how many of you have worked in GIS? Most of you. Okay. So, it's sort of the mapping tools are pretty crude compared to GIS. There are the spatial package in R can read shape files and so forth, and can export shape files. I think I don't know if there are things that R can do that GIS can't, but I know R. I don't know GIS, and I think some of the analyses we're going to do are probably easier to do in R. So, I'm going to show you spatial statistics in R, and we can depending on how many of you are also GIS whizzes, we can sort of talk about how to go back and forth between them. Yeah.
Have you tested your prediction accuracy using the measured data? Once you interpret, and then using the measured point, genes concentration, you can test your accuracy. Have you tested?
Okay, so yes, so that's a good question. So how do we test the accuracy of this fit? Because if we evaluate the interpolation at the data points, it's actually going to just return the value of the data points. So, I mean, these colors are based on evaluations at the center of each grid square. But if I actually evaluated the function at the data point,
Yeah, the weight will be so high.
then I'm just going to return the value of that data point. So we'll come back. That's an excellent question. We'll come back to that. But we can't actually, if we look at if we applied the interpolation function at the data points and asked what's the mean squared prediction error, it's 0, regardless of what prediction scheme we're using, because it's an interpolation scheme rather than a smoothing scheme. So this is with an exponent of so the p=1. So we're looking at a 1/distance simple inverse distance weighting. But what about other weightings? So here is a p is 0, and in this case, that we're just predicting the mean everywhere, right? So this is sort of the non-spatial prediction. Here is the one we just saw. Here is p equals 2. And p equals 2 is I mean, there's you can sort of make conceptual arguments for why that might be a good one too, because you know, if you think about increasing distances in two-dimensional space, right? The area of a ring of, say, you know, between distance d and d plus delta, as d gets larger, the area of that ring gets larger as the square root of d. So it might make sense, you know, so there are going to be more points in this ring than there are in this ring. So you might want to downweight that larger ring by, you know, a squared function as opposed to just the distance. So, and what we see here is that it's starting to more closely track the data, in the sense that you have, you know, deeper reds close to these low values, brighter yellows close to these high values. That's compared to here, which is sort of a smoother surface. And if we went to a really high value of p, so here's p equals 10, and what, you know, you can see it's very blocky, and to the first approximation, it's basically saying, you know, it's taking the value of the closest point. And you can see a little bit of a, you know, there's a bit of a curve. It's not a perfect step function, but it's pretty strongly just, you know, whichever the closest point is, that's the value it's taking. And so you also, yeah, you can see that here, you know, we're actually getting predictions of 7 or 7.5, right? They'll almost white colors, which really don't appear in these other interpolation schemes. So how do we decide which of these is best?
I have actually a question.
Sure.
So when the circles intersect, overlap, shouldn't the color between the two circles be the same as the color of the two circles?
Well, so remember that there's actually a point in the middle of each circle, and where the so the value is actually from that single point.
Right.
And
Now,
so,
The circles are drawn to scale of their values. So
Right.
that area doesn't really mean anything in space.
okay,
It's
so
just,
Yeah.
it's
the
just
area,
indicative of that point value.
right. Yeah. So this is not the area of sampling. This doesn't mean that we sampled a larger area here than we did here. It just means that the zinc value at that point was larger than the zinc value at that point. So there's no meaning to the overlap. Yeah, it's just I mean, the only reason they overlap is that their distance is small relative to their values. The values are large relative to the distance, but
Okay, I see.
yeah. Okay. So we can't evaluate this by asking, you know, we can't simply say, you know, we can't evaluate by asking how well it predicts the data, because if all of these predict the data perfectly. Okay.
Sample again.
Okay, right. So what we would really want to do, right, is to be able to go out and sample again in places where we haven't sampled before, and then using these fitted surfaces that are from the original data set, ask how well they predict the new data.
Or you can do like cross validation. You took one of the sample and then you interpolate and then compare your interpolation and the method point everywhere.
Right. Everybody got that? Okay, so cross-validation. So let's imagine, so basically cross-validation we can think of as the process of simulating collecting new data. And what we do is we take out some of it, let's you know, you went right to the end, but let's build it up conceptually. suppose we took half the data, set it aside, use the remaining half data to fit the interpolation, and then asked how well that interpolation predicted what's called the validation data set. So we divide the data into a training data set and a validation data set.
How do you choose which points to take out?
You typically choose them at random. Okay. And so let's, so just to, I mean, if we, go back to this example, suppose, well, so for the case of simplicity, let's suppose that we took out every other data point. Okay. And then if we had, if we had a really high value of p that led to only using the nearest data point, then if we took out the second and fourth and so forth, then our prediction would be, something like this. Okay. And then we can ask for each of these points how well it predicted. And let's suppose, so it's tricky here because the validation points are actually exactly halfway between the training data points. So let's suppose that they were slightly closer to the one in front. Okay, and so in each case we can sort of say, well, what's the residual? So there's the residual of that point. There's the residual of that point. There's the residual of that point, right? And then there's residual of that point. Okay, and then we can compare that to another scheme where we said, let's suppose it was a linear interpolation. Okay, and so now we have a different set of residuals, which in the case I've drawn happen to all be smaller. Okay, and so we can then we can calculate the mean squared error of those residuals, and our goal is to find an interpolation scheme that minimizes that. Okay, and typically we wouldn't take out an evenly spaced set of points as our training data set. We would basically pick half the points at random. Now the drawback of doing this, and this is called what we called twofold cross validation. So we're using the existing data to validate the model. Now the downside of this is that we're taking out half the data, or we're building our model with our interpolation with only half the data. So it's not going to be as good of an interpolation surface than it would be if we had used all of the data. So we can actually do we're not restricted to having just half and half. We can do n-fold cross-validation. And what that does is we divide the data set into n groups of equal size, and assign the points randomly to each of those groups. And then we take the first group and use that as the validation data set. So we build an interpolation model with the other n-1 groups, and then use it to predict that validation set. And then do the same thing for the second set, third set, and fourth set. So we have the training data set in each case is larger, right? Because it's n minus, if n is 10, then that means we're using 90% of the data to build the interpolation model. And we actually have a way of assessing it not just against half the data, but against all the data by repeating it until we've used all of each of those groups as the validation And so the sort of limit of this is to have n be the number of observations. Okay, so leave one out cross-validation. Says, let's go through, let's take out the first point, fit the interpolation model with all the other points, and predict that first point, and record the prediction error. Then put that point back in, take out the second point. Fit a new interpolation model, predict the value at that point, record the prediction. Yeah.
But that, why to use all the point to predict when you are taking just one out? That is going to be function of which kind of weight are you using. And a certain distance, that other points are not going to have any effect on that missing point you took out.
Sure. Yeah. If you know the points out here probably don't have much effect on the prediction here, but what if suppose I'm kind of skeptical about the whole that there's any spatial pattern at all, and I want to include the let's just predict the mean. Okay, so I could pick, or even I could pick a value of p that's very small that encompasses most of the data.
So to do this cross-validation first, you need to understand what is the variability, spatial variability.
No. This actually is going to be a way to evaluate. So we're going to then run this for p equals 0, p equals 1, p equals 2, p equals 3, p equals 4. Right? When p gets large, then in fact these points don't matter. But it's easier just to recalculate the whole thing anyway, if you're doing it on a computer instead of doing it by hand. And so this is actually, this is. Yeah. Otherwise, I have to keep track of not only which point I'm taking out, but where it is and which ones are its neighbors. Right? It's easier just to recalculate it.
So it's then independent of your interpolation scheme.
Well, I'm going to So I'm going to do this. If I do this I'm going to do this for each interpolation scheme. Okay. And for each interpolation scheme, if it's a really good interpolation scheme, the prediction errors will be small. If it's a bad interpolation scheme, the errors will be large. And so this is a way of assessing, or that's one axis on which an interpolation scheme could be said to be good or bad, is how large are these prediction errors. Yeah.
Does one of the cross-validation methods work better than the others? Like leave one out is better than twofold?
It's a trade-off. Leave one out is the most powerful. It sort of gets the most information out of the data. If you have a really large data set, though, it can take, or if the fitting process takes a long time for the computer to calculate, then it becomes, it can be very slow, right? So it's a question. So n basically is the number of times you have to fit the interpolation scheme to get your result. In this case, with this data set and using inverse distance methods, it's quite fast, and we can leave one out cross-validation. If we had 100,000 data points and it took the computer 10 seconds to do the fit, right, then you want to use a much smaller value of that. So that's the trade-off. This is most informative. This is cheapest. And even the twofold cross-validation, I started off saying we just have a training set and a validation set. Strictly speaking, with twofold validation, you split the data set in half. You use the first half to predict the second half, and then you flip it around and use the second half to predict the first half. it's a random draw. Okay. I mean, when you're doing leave one out cross validation, you can actually go through systematically because you're gonna, you know, it doesn't matter what order you do it in. But if you were doing twofold cross validation, instead of picking every other one like I did here, you pick half of them at random. And one of the one of the reasons that one of the reasons that leave one out cross validation is more powerful than say a twofold is, suppose your spatial pattern is your sampling pattern was such that you had a lot of observations in this area and just a few up here, right? If you picked half of these data points at random, there's a non-trivial point that your training data set is all going to be here, right? And so you're really not going to have any information out here. Whereas with the leave one out validation, at least when you're predicting this one, you know that you're going to have this one in your training data set.
This forces you to think about like the ratio to the between like the cost of data collection and the penalty associated with false prediction. Right.
Explain that more.
Because say you have like, when choosing, if you want to do twofold cross validation, right, if the cost associated with collecting every individual data point is very high, you're wasting a lot of that cost essentially, right, by eliminating half your data. But you're going to be able to validate your model to a much higher degree of precision, and thus you'll have more confidence in it. Is that true?
No.
Predictions? So
No.
So I'm trying to guess why you would ever choose like twofold cross validation when it seems like you're losing quite a bit of your data set.
Right. You're losing information with twofold cross validation. The only reason for doing that is just computational speed. Okay. Which is and the computational speed. And really the limiting factor is how long does it take to fit your model, what the model is to your training data. Okay. And if it's a quick model like this, then there's no reason to do twofold cross validation. If it's if it takes an hour, right, then
so that's the cost.
That's the cost. Yeah, it's not the cost of it's not the physical data collection. The leave one out cross validation makes the most use of the data you have.
So
Yeah.
So you will be looking at the complete data set before you go to that, right?
Yeah.
So when you look at it and if you see a very tight, tight sample,
Mm-hmm.
you don't have too much dispersion, then twofold cross validation might be okay. If your data is very dispersed, then if you want to select, if you have a choice in terms of cost and the efforts and everything and the tools you have, if you have a sample that's very tight anyway, then twofold might be.
Well, I think it's not so much the tightness of the sample, but the extent to which there's spatial pattern or in the locations of the data.
But we're looking at the sample in entirety. Will you be able to guess which cross validation scheme is better?
Well, my understanding is that leave one out always gives you the most information. It's the gold standard. And so the only reason not to use leave one out, and the larger n is in your n total cross validation, the closer you get to leave one out. And so then it's just a question of how long are you willing to wait to get the answer. Okay, and that's just a practical trade-off. There probably is some theory about this issue. I don't know that theory. I can try and find it if you're interested. So in the case here, what I did was I did leave one out, cross-validation, for a range of values of p. Okay, so for each p, so for p equals 0, right, I did leave one out, cross-validation, got a mean squared prediction error. For p equals 1, I did leave one out, cross-validation error, got mean squared prediction error. So what I get, so in terms of computations, so there's the cross-validation of a particular model, and in this case, so it's fitting that model n times, whether n is n-fold or n is, in this case, with leave one out, n is sample size, and then repeating that for a sequence of models. And so it's a way, in this case, to compare this, to evaluate, how this parameter p in the weighting scheme affects the accuracy, you could say, of the interpolation. But we could even use it to compare between completely